In this video we look at the Boxer, Inline and V-twin engine, the pros and cons of each specific to aviation, and we'll reveal the best two-cylinder engine layout for aviation use. We'll also take a closer look at a new V-twin engine for light sport aircraft, as well as a brand new, not yet released, 4-stroke inline twin airplane engine. What's up everyone, I'm a private pilot and aviation enthusiast, and this is Let's Go Aviate. Let's start with the pros and cons relating to the layout of each two-cylinder engine. The inline twin is the most compact two-cylinder engine configuration, and the Boxer twin is the least compact configuration. The Boxer twin is the widest and the inline twin the narrowest but deepest and tallest two-cylinder configuration. Then there's the V-twin, and while not as tall as the inline two, it isn't much shorter, and while not as wide as the Boxer twin, it isn't much narrower, which results in both a high and wide layout. The inline twin has another advantage. With its cylinders being right next to each other, they can share an overhead cam, which saves weight and further contributes to its compactness. The V and Boxer twins heads each needs its own overhead cam, if that's the valve mechanism in use, which means more moving parts and a bigger engine profile. All that said, two-cylinder engines are fairly small, and for pusher ultralight aircraft, layout and compactness doesn't really matter. For tractor light sport aircraft, however, the Boxer twin's low vertical height is usually the best layout, as it can be mounted right at the top of the engine cowling without impacting forward visibility. The inline two-cylinder layout naturally does impact forward visibility, but two-stroke inlines can usually be mounted upside down, as two-stroke engines doesn't have an oil sump, and that removes the visibility problem. As for the 4-stroke inline twos, these are all high revving engines, and they require a reduction drive to slow down the propeller speed. And since a redrive is required anyway, the manufacturers might as well use it to place the prop shaft basically anywhere they want. The inline engine can thus be mounted lower, right side up or slanted, with the redrive raising the prop shaft so that propeller tip ground clearance is adequate while maintaining good forward visibility. And everything I just said about the inline twin is also valid for the V-twin. So with regards to layout on tractor airplanes, the Boxer twin comes out on top, as it requires the fewest workarounds or compromises. But layout isn't the only important thing when it comes to airplane engines. Something else to consider is overall engine running smoothness, which contributes to overall engine reliability and is thus very important. The first source of engine vibration to consider is caused by the up and down movement of the pistons and connecting rods. This rapid changing of direction of mass causes vibration or imbalance and is referred to as the primary imbalance. The Boxer twin, which has a separate crank pin for each conrod, has perfect primary balance. Because the pistons' movement oppose each other, moving in and outwards together, the inertia of the moving weight is opposed and cancelled out. The inline twin with a flat plane or 180-degree crankshaft too has perfect primary balance, with one piston moving up as the other one moves down. The inertia forces are balanced out. However, these two engine layouts have perfect primary balance only in the total upwards and downwards movement of the pistons. But because these inertia forces are offset by a distance, it creates an imbalance called a rocking couple. On the inline twin, it's obvious as the cylinders are next to each other. This means the inertia of the moving pistons are trying to rotate the engine in a clockwise direction, followed by trying to rotate it in a counterclockwise direction, and repeats that rocking motion on every engine revolution. This is the same on the Boxer, as here too the crank pins are offset by a distance. Looking at the engine top down, the inertia of the pistons wants to rotate the engine to one side, then to the other. This means the Boxer and inline twin are less than perfect in terms of balance. But it doesn't end there. Another source of engine vibration is caused by the conrods going side to side as the piston moves up and down. I'm not referring to the inertia of the side to side moving conrod, as that is countered by the crankshaft counterweights. As the conroid becomes fully angled at 90 degrees and 270 degrees of rotation, it gets shorter relative to its length at 0 degrees and 180 degrees of rotation. Because the conrod gets shorter approaching 90 degrees of rotation, it pulls the piston down additionally, which causes it to accelerate more. This causes what is called the secondary imbalance. This means as the pistons move from 0 degrees to 360 degrees of crankshaft rotation, it accelerates, decelerates, decelerates and accelerates in that order. On the inline twin, with both cylinders facing the same direction and with one piston always being at the acceleration section, with the other being at the deceleration section, the secondary imbalance forces of the pistons stack up, resulting in bad secondary balance. Because the Boxer's cylinders are opposed, the secondary imbalance forces on each cylinder are opposed and the imbalance is cancelled out and gives the Boxer twin perfect secondary balance. At this point, it is important to note that both the secondary imbalance as well as the rocking couple vibrations can be removed by the use of a balance shaft. However, adding a balance shaft to an engine increases the number of moving parts, which negatively affect the reliability as well as making the engine heavier. It also increases complexity, which increases manufacturing and maintenance costs. And lastly, a balance shaft adds internal friction, which means less power, lower efficiency and worse fuel consumption. For those reasons, most manufacturers choose to not add a balance shaft unless absolutely necessary. Why is all this important for airplane engines? It's important for all engines, but airplane engines are usually operated between 75% and full power continuously, as opposed to motorbike or car engines, which are used at full throttle much more sporadically and usually averages out at less than 50% continuous use. This means airplane engines will be continuously exposed to the worst of its vibrations, which results in engine failure much sooner. For this reason, engine balance is crucial on airplane engines. A Boxer twin, often converted for aviation use, is the BMW R1200 motorbike engine. Interestingly, the early BMW Boxer engines did not have a balance shaft. But with their Boxer engines evolving, somewhere in the early 2000s, a balance shaft was added. Keep in mind, the BMW R1200 is a big twin at 1200cc, so a balance shaft being added is not that much of a surprise. Smaller Boxer twins like the HKS 700E ultralight engine, which is only 680cc in displacement, does not have or necessarily need a balance shaft, which makes them simpler engines. On inline twins like the Rotax 582 with a relatively low max RPM of 6,800, the manufacturers chose not to add a balance shaft and just live with the secondary imbalance and rocking couple vibrations. On higher revving engines like the Yamaha Phaser snowmobile engine, which often gets converted for aviation use, which revs up to 11,000 RPM, adding a balance shaft was pretty much unavoidable. We seem to be missing a two-cylinder engine. The V-twin. So how does the V-twin stack up against the Boxer and inline in terms of engine balance? On a 90-degree V-twin, where the conrods share a single crank pin, it is possible to achieve perfect primary balance. But the 90-degree V-twin achieves perfect primary balance differently to the Boxer and inline twin, as it can't use the inertia of one piston to cancel out the inertia of the other. Instead, it uses the crankshaft counterweights to counter the piston inertia. Usually, the crankshaft counterweights is mostly used to counter the inertia of the side-to-side moving conrod, but in the 90-degree V-twin, it is possible to counter both the conrods as well as the pistons. When one piston is at top dead center, the counterbalance opposes the piston as well as the other conrod. And as the crankshaft rotates 90 degrees, and the counterweight now opposes the piston as well as the other conrod. I don't want to go too deep into the balance of the 90-degree V-twin, because the new aviation V-twin we are looking at is an 80-degree V-twin. It is the Aeromarine Hybrid V-twin. It's a 800cc liquid-cooled 4-stroke 60 horsepower V-twin. And as I said, the angle between the cylinders is 80 degrees. The biggest reason why V-twins gets made at less than 90 degrees are because the smaller the angle, the narrower the engine is. A wide engine isn't usually much of an issue on aircraft, but it usually is an issue on motorbikes. While there is very little information on the website about the inner workings of this engine, there is enough information for us to make some reliable assumptions. And here is the interesting bit. We have an exclusive agreement with the manufacturer of a Can-Am style V-twin engine. Now, obviously it has been modified, but it is just uncanny how much this engine looks like the Rotax 4Tech Can-Am V-twin ATV engine. And I suspect it is because it is exactly the same engine. This of course explains why it is an 80-degree V-twin and not the better angle of 90 degrees, which is because it was designed for ATVs. As it is an 80-degree V-twin sharing a single crank pin, it cannot have perfect primary balance. But while its primary balance isn't perfect, it isn't actually all that bad and is only a little bit off when compared to a 90-degree V-twin. What about secondary balance? Because the cylinders doesn't directly oppose each other, the secondary forces doesn't cancel out like on the Boxer twin, but it doesn't stack up like on the Inline twin either, as both cylinders don't point in the same direction. Since piston 1's secondary imbalance is in an upwards direction away from the crankshaft and piston 2's secondary imbalance is in a downwards direction towards the crankshaft, the resultant secondary imbalance force is in a sideways direction, switching from one side to the other. This results in a secondary imbalance that isn't as good as the Boxer twin, but is better than the Inline twin. Looking at the overall balance for each layout, the Boxer twin and V-twin comes out on top, with the Inline twin losing out. But this is still not the end of it, as there is one more vital piece that contributes to an overall smooth running engine, and that is firing interval. Firing interval refers to how much the crankshaft rotates between spark plug fires on each cylinder. An even firing interval is important for smooth and even torque delivery to the propeller. An uneven firing interval usually means a larger flywheel is required to smooth out torque pulses. The Boxer twin has an even firing interval with one piston cycle between each cylinder firing. When cylinder 1 fires, the crankshaft makes a full 360-degree revolution before cylinder 2 fires, and then 360 degrees before cylinder 1 fires again, and the cycle repeats. The firing interval on a flat plane or 180-degree crankshaft inline twin does not have a smooth firing interval. When cylinder 1 fires, the crankshaft turns 180 degrees and fires cylinder 2. Then a whole 540 degrees of crankshaft rotation is necessary before cylinder 1 fires again and repeats the process. That is of course only true of 4-stroke inline twins, as 2-stroke inline twins would have an even firing interval of 180-180. The 80-degree V-twin's firing interval is less even than the Boxer twin, but more even than the 4-stroke inline twin. Cylinder 1 fires and then 280 degrees of crankshaft rotation later, cylinder 2 fires. Then 440 degrees of crankshaft rotation is required before cylinder 1 fires again and repeats the process. So with regards to an overall engine running smoothness comparison, the results would look like this. The Boxer twin is the clear winner and the 4-stroke inline twin the clear loser. Keep in mind the specific engines mentioned isn't necessarily an apples to apples comparison. For example, the BMW R1200, which is a Boxer twin and is the smoothest running of the twins, yet it requires a balanced shaft. This is because it is a 1200cc engine with relatively big and heavy pistons and conrods, compared to the other engines mentioned in the video, which are all between 500 and 800cc. The bigger the pistons, the heavier they are and the bigger the imbalance forces. By keeping the displacement of these engines small, the imbalance forces can usually be tolerated without requiring a balanced shaft. This illustrates the point I'm trying to make. Just because an engine's layout is inherently unbalanced doesn't mean it is a bad engine. One example of this is the inline twin Rotax 503 and 582, which combined sold more than 60,000 units and were clearly very successful. Even in 4-stroke form, inline twins like the Yamaha Phaser snowmobile engine seems to be quite popular to convert for aviation use. It is even looking like Yamaha might start producing an inline twin specifically for airplanes. In 2021, Yamaha formed a partnership with Shinmeiwa to produce light airplanes and engines and did its first test flight in 2022, powered by a 500cc inline twin 4-stroke engine. It isn't confirmed that this will be the engine they produce for their light aircraft, but the engine used is very likely based on, or at least very similar to, their Phaser 500 snowmobile engine. And if that is the case, it is a fuel-injected, liquid-cooled, double overhead cam engine with a max RPM of around 11,000. It will most likely be a flat plane or 180-degree crankshaft engine, which means it will have good primary balance other than for the rocking couple. And it will have bad secondary imbalance, but that will be severely reduced by the addition of a balanced shaft, and it will overall be a fairly well-balanced engine. The inline twin actually has so much horsepower per pound that the addition of a balance shaft isn't a big deal. While it doesn't have record-breaking horsepower per cubic centimeter, 80 horsepower from 500cc is nothing to scoff at. I hope you enjoyed this video on 2-cylinder airplane engines. Leave a comment below and let me know what your favorite 2-cylinder engine is for aviation use. And see you in the next one.